So friends, in the previous slide, we learnt various aspects of set. We ended the last slide with what is a complementary set. And as discussed, now we'll be talking about union of two sets and intersection of two sets. And based on these principles, based on these concepts, we are going to move on further in knowing a few more properties about sets and end this particular section of sets with the De Morgan's principle. So let's start with the first thing. As I said, let's understand what is union of two sets. So basically, union of two sets, let's say if we have two sets A and B, then the set which is the union of these two sets is represented by A union B. So this U symbol over here represents the union of the two sets that are besiding this particular symbol. So NAUB represents union of two sets. Now, if I want to write this particular set in the forms that we have earlier discussed, this has to be written as X represents, where X is an element of A, or X is an element of B. So let's try and understand what this particular roster form tells us. It tells us that every element X is a part of the set A, or that element X is a part of set B. So or is the keyword over here. We need to understand that element X needs to be either here or here, right? So, and also it also signifies that it can be a part of both of them as well. So let's have a diagrammatic representation of A union B. So in that case, let's say if you have a set A over here, right? Let's say if this circle represents set A, and this circle over here represents set B, right? Then A union B is going to be all the elements lying inside this region. So let's try and understand that with a shaded. So this is how it is going to work. So this entire region will represent A union B, union of two sets A and B. Now let's try and understand this from a formula perspective. If I want to find out N of A union B, number of elements in A union B, it is going to be equal to number of elements in the set A plus number of elements in the set B minus number of elements in the set A intersection B. Now this is where the next thing is going to come in picture. The next concept is going to come in picture, which is the intersection. So what we will do is first understand what intersection of sets is and then come back to this formula. So the second concept, as I said, is going to be the intersection of two sets. And as written in the formula, the intersection of two sets is symbolized by the symbol of reverse U. Like we have U to represent union, the reverse U represents the intersection of two sets. So A intersection B, reverse U B means intersection B, is going to be equal to every element X in this particular set has to be in the set A, and also at the same time it has to be in the set B. So this is how we write the intersection of two sets A and B. Now if I go back to this particular diagram, this particular Venn diagram so to say, then A intersection B is represented by this particular region. So this region over here will represent the A intersection B. All the reason because this region involves all those elements which are a part of set A, and at the same time they are also a part of set B, and that is why this region will be represented by A intersection B. Now let's try and go back to the formula. If we go back to the formula of number of elements of A union B, you will see that the first two elements are N of A all the elements which lie here, added to it we have all the elements which lie in the set B. Now in this process you will notice that this region, this mid region, which is nothing but the intersection of A and B, appears twice, gets added twice, right? Because once it gets added when you count A, and again it gets added when you count B. So we need to subtract it once, because n of A union B, the union of these two sets, is nothing but this entire area. And when I say this entire area, all of this region has to appear once, right? So n of A has appeared once, n of B has appeared once, but in that process this mid region has appeared twice, has been counted twice. So that is the reason we have to eliminate one of them, right? So that is why we have minus n of A intersection B, and that is why the formula number of elements A union B is equal to number of elements in A plus number of elements in B minus of number of elements of A intersection B. And naturally, when I take it this side, number of elements of A intersection B, the formula works this way: number of elements of A plus number of elements of B minus number of elements of A union B. Again, this is a simple enough formula to understand from the diagrammatic point of view as well. So these are the two formulae for finding out the union set of A and B and the intersection set of A and B, and this is how the diagrammatic representation works. Now let's move to the next concept that we have to learn in this series, and that is about difference of two sets, right? So difference of sets. Now as the word itself suggests, difference is going to be simply the set A minus the set B. If we treat it that way, we can also have B minus A as well, but let's first understand what A minus B is going to be. So A minus B represents the difference of sets A and B in that particular order. So as it says, A minus B. So if we have to write it in that particular form, so X has to be in A and X should not be in B. That is how we write it because this clearly says that we want all the elements of A, but those elements should not be a part of the set B. So if I want to draw a diagrammatic representation of it, if this is set A and this is set B, let's say, I'll write set A over here, set B over here. Now clearly, according to the definition of the difference of sets A minus B, the region what we are interested in is this particular region. And carefully, as we can see, we don't have to include the intersection because the intersection is a part of set B, and we have to make sure that no element in the set B has to be included in this particular thing. Now likewise, if I want to write B minus A, let's use a blue marker for that. B minus A is going to be equal to every element X where X is a part of B and at the same time X is not a part of A. This is how B minus A is defined, and if I want to represent it here with the same blue marker, this is how it will work. So this region is B minus A and this region is A minus B. Now on this note, if we have to understand what a symmetric difference of sets means, symmetric difference of sets. Now that particular thing is nothing but A triangle B. This is how we represent the symmetric difference of sets, and symmetric difference of sets is nothing but, by the formula, this is going to be nothing but equal to number of elements in A minus B plus number of elements in B minus A. Right? So basically when you have two sets A and B, then you first find out what A minus B is, then you find out what B minus A is, and then simply add them, and then you will get the symmetric difference of both these sets. So basically n of A triangle B is nothing but this region, the pink region over here, added to that the blue region over here. Now let's see if we can derive another formula for it. Definitely we can. What we have to do is, now from the diagram it is quite clear that we can write this as n of A union B minus of n of A intersection B. Let's try and understand how have we derived this. Now symmetric difference of sets, as we just discussed, is nothing but this region, the pink region, added to the blue region. Now this entire region over here, as we have discussed earlier, is nothing but A union B, right? Now from A union B, the only region that we don't want is the intersection region. So that's what we have done. Number of elements of A union B subtracted to number of elements in A intersection B, and hence we get the symmetric difference of two sets. So this is about symmetric difference of two sets. Now there is one more thing that I want to discuss, and that is number of elements of A union B union C. Now this is slightly tricky. We are involving three sets in this particular thing. So let's see what the formula gives us. Here this is going to be equal to, first let me give you the formula. It is going to be number of elements of A plus number of elements of B plus number of elements of C, right? After that we have minus of number of elements of A intersection B minus number of elements of A intersection C minus number of elements of B intersection C plus number of elements of A intersection B intersection C. Now why have I done this? I have done this because I guess till now you are pretty clear about what union is, what intersection is. So let's dive into a situation where we have three sets, right? And let's understand this formula from the point of view of a Venn diagram. So let's have a Venn diagram over here. So let this be set A, let this region be set B, and let this region be set C, right? Let me just simply mark them down. This is set A, this is set B, and this is set C. Now what we want in A union B union C is this entire region out here, right? All of this counted once will give me A union B union C, right? So in the formula as mentioned, what we have done is added A to B to C. So when we add these three things, it is quite clear that this region has been counted once, definitely. I'm not going into the intersection region at all. I'm just counting that region which is devoid of other sets. So basically I'm just counting A, which does not involve B and C. I'm again counting B, which does not involve A and C. And finally I'm counting C, which does not involve A and B. So this region is definitely counted, but apart from that, these regions are also counted. Let us go back here again. N of A plus N of B plus N of C basically means this entire circle plus this circle plus this circle as well, right? So while doing this particular addition, what is happening is A intersection B, this region is getting added twice. At the same time, this region A intersection C is getting added twice again. Likewise, B intersection C, this region is also getting added twice. So if you carefully notice, you will see that these three regions are getting added twice. So definitely we have to subtract them once, right? So that is why we have minus N A intersection B minus N A intersection C minus N B intersection C. So now what is happening is this central region in the first step of the formula, when we are adding the number of elements of set A to number of elements of set B to number of elements of set C, this central region is getting added thrice actually, right? Because this part, number of elements of A intersection B intersection C, is actually a part of all the three sets. So when you are doing n of A plus n of B plus n of C, this mid part, the central part, is added thrice, and these three regions are getting added twice. So because we want all of them only once, we are subtracting with n of A intersection B minus n of A intersection C minus n of B intersection C. So when you do this second step of the formula, you are eliminating this once, and this once. So basically now you have taken care of this region, and this region. So all these three regions now are counted once, because earlier in the first step they were counted twice. So now they are counted once, because once you have already subtracted them. Now when you are subtracting them, what you are actually doing is you are subtracting this central region also, and coincidentally you are subtracting them thrice, because you are doing minus n of A intersection B minus n of A intersection C minus n of B intersection C. So while you are subtracting them, you are subtracting the central region thrice. In the first step you had added this central region thrice. In the second step you have subtracted that second central region thrice. So now in totality, that central region is not counted even once, and that is the whole reason we have that last step of the formula, which adds n of A intersection B intersection C once to this entire thing. So the number of elements of A union B union C is nothing but n of A plus n of B plus n of C minus n of A intersection B minus n of A intersection C minus n of B intersection C plus n of A intersection B intersection C, and that is how this particular formula works for the union of three sets. Now after understanding this interesting thing, let's move on to the next thing, as I discussed a few properties of sets. So the first thing that I want to discuss is the commutative property. Now this particular word commutative you are definitely going to come across in various chapters for different agendas of mathematics that we are going to discuss, different chapters in mathematics. You might have even come across this particular thing. Commutative is simply reversing the order. So basically sets, the union of two sets is commutative, and intersection of two sets is also commutative. What it means is basically A union B is simply equal to B union A, right? Do we agree to this? It's very easy to understand from a Venn diagram perspective as well. A union B is going to be the same thing as B union A, right? And that is why union of two sets is definitely commutative. And likewise, A intersection B is also going to be B intersection A. That means both the union of two sets and the intersection of two sets, both of them are commutative in nature. What it means is basically this particular function, this particular symbol U, if kept constant, and these two things, if you reverse, the operation, the output still remains the same, and hence union is commutative, and likewise intersection of two sets is also commutative. Now let's move to the next thing, which is the associative property. To discuss associative property, we need to consider three sets. So what it says is, if A union of another set which represents B union C, this is equal to A union B as a set which is made to have a union with the third set C. Now with the help of Venn diagrams, finding out that on either sides of the equality both these things are absolutely equal suggests that union of sets in this particular fashion is associative in nature. So this proves that the union of sets has an associative property. Now likewise, we can have this for the intersection as well. If you have A intersection B intersection C, now you can use this particular thing as well to prove this, what we are trying to do. This is going to be same as A intersection B intersection C. Now again, because both these things are absolutely equal, you can say that intersection of sets does have an associative property with it. Now moving on further, talking about the distributive property. Now this is an interesting one, because here what happens is there is a slight change when it comes to the union and intersection. So basically, if we have A union B intersection C, what is going to happen is when you distribute this particular thing, you are going to get A union B, right, as a set, intersection to A union C. So this is what happens when you distribute a particular union symbol to another set which is having an intersection of two sets B and C in this particular case. Now going to the reverse thing of this particular thing, if you have A intersection B union C, right, what happens here is we are going to get A intersection B. Now this set is going to have a union with A intersection C. So this is how distribution works when it comes to union and intersection. So the union has a distribution with the intersection, and the intersection has a distribution with the union. So this is how the distributive property works. When it comes to union and intersection, they have a distribution with respect to intersection and union respectively. So these are three key properties when it comes to sets for commutative, associative and distributive properties. Now the last and the most important thing that we are going to discuss in this section of sets, so that you can attempt a few problems in the section of sets in the Plance's module, is the De Morgan's principle. Now the De Morgan's principle again is a formula or an analysis with the help of Venn diagrams. The formula is something which I am going to give you first. Later on we can see the Venn diagram and analyze accordingly. So here it goes. If A and B are two sets, then we can write A union B, the complementary set to this. Try and understand, we have a set A union B. If we have a complementary set to that, then this is going to be equal to A complement intersection to B complement. Before understanding this formula, let's have the second formula as well under the De Morgan's principle, which is similar but absolutely opposite. So if we have A intersection B, now in place of A union B we have A intersection B, and if we have the complement of that set, what we have is A complement union of B complement. As I said, these two formulae are similar but entirely opposite because of the nature of the functions that have been used. Now let's move to the Venn diagram to understand how these formulae have been exactly derived. For that matter, you can also refer to the Plance's module. We have an algebraic point of view for deriving these formulae, but the simple version of this is the Venn diagram, because you can clearly see how exactly these things have been derived. So let's have two sets. This is set A, my dear friends, and this is set B. So this is set A, this is set B, right? Now if you consider, now since you are considering a complement of this particular set, we need to have a universal set. So we will have a rectangle which generally represents the universal set, so that to understand that there are a few elements which are outside the A union B region as well. So now when you say A union B complement, the complement of this particular set, A union B is this entire region, right? So A union B complement is going to be everything outside this, right, lying in this rectangle. So basically, just to have a small understanding of that, I'm just representing it with a few dots. Now this dotted region symbolizes A union B complement, right? Now let's see the other side of it. The other side of it says A complement intersection B complement. Now if you think of A complement, it is going to be everything outside this circle, right? Everything outside this circle means this, including this as well, including this part of B as well, which is nothing but B minus A, right? We have discussed this. So basically, A complement is everything in this dotted pink region plus this region over here, which is B minus A. Now, to that, you have an intersection of B complement. Let's try and understand what B complement is. Now, since this is B, B complement is going to be everything outside this region, right? So, everything outside B is going to be B complement. So, B complement is going to be this entire pink dotted region plus this region over here, which is A minus B, right? So I hope you have noted down these two entities, A complement and B complement, what those two are. Now, if you intersect those two regions, you will understand that this intersecting with this entire thing will eventually give you this pink dotted region, because if you want an element to be part of A complement and B complement both at the same time, that has to be this pink dotted region from the understanding of what A complement is and B complement is. Now, using the same thought process, let's go to the second formula. The second formula says A intersection B complement. So first of all, A intersection B is this region, right? This central region is A intersection B. Now, if you want the complement of that, it is going to be everything outside this region in the universal set. So that is going to be this pink dotted region, including all of this as well, because what we want here is everything in the universal set apart from this central region. So this all is A intersection B complement. Now let's see the other side of the formula. The other side of the formula says A complement. Now we have already discussed what A complement is. A complement is this region, everything outside A basically. If you want a union of that with B complement, which is everything outside B in this region, you will eventually end up with the pink dotted region again. Because if you want a union of two sets, as we have discussed, union is nothing but every element in the first set or in the second set. So it can be a part of both of them, and hence if you want A complement, this all region has been already covered. Now if you want B complement, all of this has been covered. So even this thing has been included, and hence in totality all of this except for the central region is included in A complement union B complement. So hence it justifies the formula, the De Morgan's principle. So here we end this concepts of sets that kickstarts the journey of relations and functions. But before ending, one small thing, although I am pretty certain that you guys will be able to understand this on your own, but just one thing in this entire thing that we have discussed, if the sets A and B, right? Now this is the right time to understand this, because you have already understood what union and intersection is, also from the point of view of Venn diagrams. If the two sets A and B are disjoint sets, right? We have earlier discussed what disjoint sets are. Disjoint sets are nothing but something like this, right? If A is this and B is this, they don't have an intersection is what disjoint sets mean. So if these two sets don't have anything in common, right? So clearly number of elements of A intersection B is going to be 0, and hence number of elements of A union B is clearly going to be n of A plus n of B, because this part is going to be 0, and that is how the other formulae are also going to adjust accordingly. For disjoint sets, specifically number of elements of A intersection B has to be 0, and accordingly we can understand the other things. So friends, here we end the concepts of sets. So now when we know sets, let's move on to the more important and more interesting part of this chapter, which is relations and functions. So to kickstart with, we will understand the key difference between relation and function, the key meaning of what a relation is and what a function is, and hence know other aspects about them.